Are there any doubts or not? Okay, so no, that is fine. Okay, if you have any like you can like speak through. You can unmute and ask. Uh, yeah, right. So we were talking about uh, the what happens like how you are trying to solve a quantum system, because we were talking about some quantum particles in some external constant magnetic field. uh, their like they behave, or their quantum nature is something very interesting, which give rise to something called Landau levels. So which we will be looking into. Uh, this is something which we like quickly went through last time around. So we'll try to see like what was going, and we'll try to finish from where we left that day. And yeah, so we were considering some like magnetic field, a constant magnetic field, and see this magnetic field is along uh, uh, z direction. So it is along uh, uh, z direction. So uh, if you have a magnetic field, if you have a constant magnetic field, and let's say if for a general electromagnetic system classically, if someone asks you to write a Lagrangian, so the Lagrangian for that system would be this. So this part half m x dot square. This is your vector. So this will be um, your kinetic part, and then your potential part will contain these two terms. So one, this A is your vector potential, and phi is basically your scalar potential. So this is what in classical dynamics you have learned this. So you have gone through how to treat electromagnetic systems classically. So that is something you have studied very well in before. So then uh, if you have a Lagrangian like this, if you define classically a Lagrangian for a electromagnetic system like this, then what are the equation of motions? So for equation of motions for any electromagnetic system is obviously Maxwell's equations. So even if you to derive an equation of motion from the Lagrangian, you basically use Euler-Lagrange equation. So this is Euler's Lagrange equation. So from Euler's Lagrange equation, you will find this. This is basically your Lorentz force. Uh, I hope you have seen this before. So this is how the charged particle would behave. We are talking about this charged particle is something, a quantum particle, like an electron or some other particle which has charge and could also have some spin. So this is how a charged particle would go through in presence of some external electromagnetic field. So here uh, you have E. Let's say E is also some constant, and magnetic field which we have chosen here to be constant along z direction. Then you from this Lorentz equation, like you can calculate the what is the equation of motion along x direction, along y. So it has all three components. So this x vector, so is this is the x vector. So and when you solve this and this equation, these are basically, you can see these are coupled equations. If you solve these coupled equations, you can get the solution something like this. So something form of oscillatory, or yeah. So where omega b is your cyclotron frequency. uh, this like for example, when a charged particle moves in a magnetic field. So if you think of some uh, if you think of the magnetic field, constant magnetic field along some z direction, then uh, then there will be let me so you have some magnetic field B, then a constant magnetic field. A charged particle can go in circular path. So this circular path, if you calculate the frequency, uh, so basically, or in other words, if you want to know the time period, or the frequency with which it completes like one revolution, so that is something called as cyclotron frequency. This uh, omega b, which is this. So this is what with from where you can get the time period. So that is how you see that. I think you are all aware of this dynamics of a charged particle in a constant external magnetic field. Then, if you want to calculate the momentum, generalized momentum associated with the particle, then you take the derivative of Lagrangian with respect to this with respect to the derivative of generalized coordinate. So then you get mx dot. So this is like your velocity mv plus q times a. A is your vector potential. So right. So I think you are aware of this magnetic field. Like is magnetic field is related with your vector potential as something curl of it. So yeah. So now you have got uh, generalized momentum, and also you have got Lagrangian. Using them, you can write. So let me call this. Um, this is some equation one, and this is equation two. So now using one and two, you can write your Hamiltonian to be this. So now that is what you know classically how you find a Hamiltonian system. So how you can get a Hamiltonian for a charged particle in some constant external magnetic field. And further, we call this A and phi are uh, gauge fields, because if you transform something phi as this, these are called some local transformations. So these are for this transformation, like for example, if you change the phi of your system by some phi minus del alpha by del t, and alpha is some scalar, alpha is some scalar quantity. So it depends on position and time. So if you transform your phi to some phi minus del alpha by del t, and a to a plus grad alpha, then you will find this under this transformation you will I mean your theory will be invariant, in the sense it means you will still able to see that uh, I mean your dynamics will still remain unchanged, or in other words, like your Maxwell's equations will not vary. I mean your Maxwell's equations will remain invariant. So your equation of motion and Maxwell equations, all these things are are basically invariant under this transformation. So that is why this and this. So so that is why these are called some gauge transformations, and it has very important implications. Today we'll also see like how this would play a role in our discussion. So so taking that in mind, we will see, suppose if a magnetic field is given, uh, like as we said, a magnetic field is given something b naught, uh, along z direction, then you can write a vector potential. Uh, you can write a vector potential like this, which means you can write a vector potential uh, which has only you can write a vector potential which has some component along yk, because suppose if you are given some magnetic field and it is in some z direction, and you are asked to write what is the vector potential. So the only way which you can construct the vector potential is from the this relation. So if you work out this relation, you can find that uh, your A should be something XB, and also you will find that if you choose this A equal to be XB, and when you transform your phi and A to be something of this form, you will still able to prove this relation B equal to curl of A, because this magnetic field itself comes from the this relation itself comes from one of the Maxwell's law, which I think you are aware of, that is um, uh, like we know this gradient or basically the divergence of magnetic field is zero. So from here only you write a identity. You say that there exists an identity. If B is something curl of some other vector, then this statement is valid. So from there you get the definition of vector potential. So right, and for simplicity we can choose phi equals to zero for the moment, and then this will help us to reduce the problem more. So then Hamiltonian will be like the Hamiltonian which we written down here, since we are not considering phi here, so phi will go away, and this phi term will go away, and you are left with this Hamiltonian. And then if you write down the all the components of A, so which we have only one component, that is QBX. So uh, so if you write down this Hamiltonian, so this is what you will get the Hamiltonian. Now, um, so now to in quantum mechanics, how will you see this? Like so for quantum mechanics, you first need the Hamiltonian, which is you have already defined here. So you defined your Hamiltonian to be this. Then uh, um, in quantum mechanics, you want something. You are looking for a system to a quantum particle is in some extra magnetic field. So for that system, you have to define a state, and to define a state, you have to use Schrodinger equation. So suppose um, you think this Hamiltonian has some um, so okay. So one thing note here that we are not taking any time dependence here. So your Hamiltonian is completely time independent. Let me okay. So so in quantum mechanics, you define like since your, I mean, uh, the Hamiltonian is time independent. So from time independent Schrodinger equation, you can write this following. So your Hamiltonian is this, and then you act this on psi, and you will find a uh, eigenvalue equation. So this E will be basically your energy eigenvalues. So that is what we'll see here. So if you carefully look, this Hamiltonian, which is given by this right here. So this Hamiltonian, if you commute with Py, and also if you commute with pz, you will find that their commutator is zero. So this tells that both I mean, this tells that uh, hello, was there any doubt, or okay, if you are not having any problem, you can speak, you can unmute and ask, or any other problem, you can just simply unmute yourself. So yeah, so I was telling, so first of all, like I'm able to audible to all, right? uh, I'm properly audible, right? You can hear me. uh, Anyone could, uh, Dinesh, Kuna, uh, Surajit, like I'm audible, right? Or uh, yes or no, anything. Or okay, yeah, thanks. So yeah, I was telling that if you have a Hamiltonian, if you so your Hamiltonian is this when you are taking commutator with py and pz. So when you take commutator with py and pz, uh, you find that your commutator is zero. So what does it tells that? It tells that both py and h have common eigenstates, and it also tells that uh, it is translation invariant, in the sense that if you uh, uh, I hope you are aware of this term, this translation invariant. So this means that if you make some transformation, for example, if you make y to go y plus y naught, or if you uh, make z going to z plus z naught, then uh, your dynamic still remains invariant. So so something, if you have like uh, yeah, so similarly, if you have something like ly commutator with h uh, is zero, then this means that if you rotate your system, then uh, this means rotational invariant. So this means you have rotation symmetry in your system. So similarly, this is what uh, your translation invariance means. So what this tells you that if your Hamiltonian is this and it satisfy these two properties here, then it means you can write down the solution for the Schrodinger equation, which you need to find what is psi. So you can write down psi something first as this form, exponential uh, ikyy plus ikzz. So why you can write down this like this part. Uh, so uh, so you can write down this part, then multiply it with this chi of x. So so suppose if you define your momentum operator as this. So this is what the momentum operator is defined as Py as IH bar uh, del by del by, and this is for Px. So this is just simply the momentum operator definition. Now, if you operate this, if you are like this is what you are uh, assuming, or you are giving an answers to your solution to your solution for this Schrodinger equation. This is a Schrodinger equation, and since you find this commutator of Py and H and Pz and H is zero, then you are telling that you can have a valued solution if you define this as your solution, where it has y and z part as something exponential of I, like plane wave solution, uh, and chi of x. I mean, you can do that because suppose if you, like for example, if you only consider the x part of this Schrodinger equation, so only uh, x direction if you consider, then your Schrodinger equation would be something px square over 2m. Uh, Only you will have the x part. Uh, Not let's say x is not actually invariant. So y. So if you take y, so it is like py square 2m equals to uh, so psi e psi. So and for similarly for z direction it would be something pz squared over 2m psi then e psi. So this is like if you calculate the solution, so it would be just simply uh, uh, so you first write down in terms of operator form. So in terms of operator form, it would be something minus h bar square over 2m del square psi over del x square equal to e psi. So the solution would be something of exponential uh, ik x. So this would be ikxx. So let's say this is ex or something. This is e. So sorry, like I'm keep writing this x, which is not true. So this will be y. Yeah. So this is y. And let's say this is something ey. So this will be something iky y. Similarly, here also, this would give you something exponential I k z z. So these are your uh, uh, so these are your basically your plane wave type solution. So that is what uh, we have written the first part. So and then we are considering it has some x part, uh, which we are calling it as something chi, which we have to estimate. But from the dependence of solution in terms of y and z, it will be surely exponential iky and exponential ikz, which I just told you that this is what generally you have it as the solution for a these are basically solution of free particle. So along y and z, you can since you have free particle type behavior, you can write down your final solution as some product of these two things, exponential of iky and ikzz. So so that is what it is written. So then what you can do, so then you can also see that when you operate uh, py on psi x, it gives you hky psi x and px, so this is again this should be z. Yeah, yeah, this is, so this is x, and or you can also write this thing also as uh, psi x y z. So this will be pz z, so pz, and this is hkz, right. So this is how your uh, uh, I mean your momentum operator would operate when you operate on psi. It will be this. So similarly, if you operate your h operator, h on psi x, it will also give you e psi x. So now this is something like very familiar to you. Like if you see, uh, I mean this, I mean these three equations, like uh, equation, this equation, this and this, all these three equations, they all have same eigenstate psi. So that is why we were having this relation, this commutator relation. So that is why these commutations were zero. And as we said, like uh, both py and h have common eigenstate, and similarly here also both pz and h have common eigenstates. So so then like our next task is to calculate what is chi. So as we said, uh, let me like make some spaces here, it is getting uh, so okay. So So yeah, uh, so yeah, H P Y P Z have all common side. So then, what you can do to determine. So now your task is to determine this chi. So to get this, you put this in Schrodinger equation. So this is your uh, Schrodinger equation, equation A, time independent Schrodinger equation. If you put B and A using B in A, so if you do that, like you will get this relation H tilde chi of x equals to e minus h bar square k z square over 2m chi of x, where h is, so you can just check this, you uh, where your h is simply 1 over 2m px square. So this h tilde, sorry, uh, m omega b square over 2 x minus ky lb square whole square. So this means I have just substituted this equation B in equation A, and then I'm writing down the Hamiltonian slightly in different way, and where this omega B, as we said earlier, omega B is your cyclotron frequency. It is QB over so it is QB over M, and this LB is a new quantity which we are defining here as something h bar over QB. It takes the unit of length, and you can call this as something uh, magnetic length. Now you can see this h tilde, uh, this h tilde looks like a harmonic oscillator Hamiltonian. Like you have something px square to m and half m omega square x square. Then you can see this is something like shifted harmonic oscillator. Shifted harmonic oscillator. So for shifted harmonic oscillator, if you recall, the Hamiltonian used to be something this uh, p square over 2m uh, plus p square over 2m plus, let's say I'm only talking about one direction, 1 over 2 m omega square x minus x naught. So this is like a harmonic oscillator. If you draw the potential, so this is your uh, potential part v of x. So it is like uh, shifted to some or yeah, yeah. So this is like your x naught. So usually you find a potential at zero, I mean, which is symmetric about zero, this harmonic oscillator potential, but now this is shifted. So this mean position of the usual harmonic oscillator is now shifted by x naught. So this is what you can see this Hamiltonian looks like. So, but you can see that this is only along x direction. But in if you see, yeah, this is only along x direction. So you can think of your system now, the charge particle which is moving in a constant magnetic field, as some harmonic oscillator system exists in x direction, but there is something even more in z direction also. So that is what uh, uh, you can see. This energy is not uh, because when you do harmonic oscillator system, you find exactly h psi equal to e psi. So there is no e minus some other extra term which you are getting here. So now if you see this thing, uh, your energy for uh, the energy, you can write it down like this is exactly yeah, this is exactly like you see in harmonic oscillator system also. So energy, you can write it as uh, let's say if h tilde chi equal to e minus h bar square k z square over 2m chi, then from harmonic oscillator, from harmonic oscillator system, this energy e minus h bar square k z square over 2m should be equals to something n plus half h bar omega, and here we have omega is omega b. So this is omega b. So from here you find that your energies eigenvalues are basically n plus half h bar omega b plus h bar square k z square over 2m. So these are your energy eigenvalues for your uh, this charged particle in the constant magnetic field. And similarly, since this also obeys harmonic oscillator system, so you can write down psi as something with some normalization. You can write it down as uh, so this chi of x now this chi of x for harmonic oscillator, you again know the wave function is given in some form of Hermite polynomial hn. Here, instead of x, it will be it was something uh, x minus x naught. So it will be ky over lb square, then exponential. So you used to write for a normal harmonic oscillator system for like when x naught is 0, when this x naught is 0, then the wave function used to be something psi x equals to hn x and exponential minus alpha x square, something of this form. So but now since you have x naught which is shifted, so it will be, instead of x minus 0, it will be x minus x naught. So that is why in this exponential part, which is basically the Gaussian form, here also it will be shifted over 2l b square. So this is what chi should be, and therefore your psi, which was given as something exponential, this implies your psi will be I, which we defined at the beginning here, ikyy plus ikzz, then chi ikyy plus ikzz, then hn and exponential. Yeah, so yeah, this will be maybe so I think x minus, uh, let me call this as x naught, x minus x naught, where x naught equal to ky lb square. So finally, you found this wave function for a charged particle in some constant external magnetic field. So it follows the dynamics similar to a harmonic oscillator system. So any question, any doubts you can, uh, like any problem, anything you didn't get. Uh, okay, so but if you want to see one interesting thing right here, these are like um, unlike it is not completely harmonic oscillator system. Like you are seeing that this is the dynamics follows a similar pattern like harmonic oscillator, other than like for example, if you look into the wave function of this, if you look into this wave function and the wave function of harmonic oscillator, the only difference you will find will be this factor, which you do not get in harmonic oscillator system. In energy eigenvalues also, if you see in normal harmonic oscillator, you get this term, but you don't have this additional extra term. So that is the difference you can see between a system of which is system between a system of a quantum particle which is in some harmonic oscillator potential and a quantum particle which is in some external magnetic field, and that quantum particle, let's think that it has some charge. So you can see like how interestingly their differences and their similarities are. So one thing here, as I was telling, it is as it is not exactly harmonic oscillator system. So what you can see, suppose if you uh, take any energy eigenvalue, like let's say for n equals to zero, or uh, let's think of this as like let's restrict the particles with kz along zero. So there is no it's like you can think of in like across kz, the potential barrier is something infinite, and you are I mean by hand you are actually restricting this such that your energy then becomes h omega p n plus half. So now it is exactly like uh, uh, harmonic oscillator system, like harmonic oscillator system. So then what you find here, so for n equals to, let's say um, when uh, n equals to 0, let's uh, take n equals to 0. So your energy is half h bar omega p. So this energy should corresponds to uh, so this is you have calculated for, if you calling this as hn, this is like uh, e0. So your size 0 should be something h0 Hermite polynomial, then and this actually this exponential part, this becomes one. Like I'm talking about the ground state wave function of hydrogen atom. So or basically not this, I mean this will remain something as alpha x square, but this thing becomes 1. So that is what the ground state of harmonic oscillator is. But the thing is, like, this is true uh, for harmonic oscillator system HO. But here, if you see here, for E0, your psi has two quantum numbers. Like psi depends on, uh, like you have made kz to be 0. So this is your psi. Let me write down your psi as exponential iky, uh, then iky by, then h0, let's say, then exponential minus x naught square over lb square, 2 lb square. So you can see, unlike harmonic oscillator system, here it also depends on ky, which means, like, for n equals to 0, ky can have has many different possible values. So ky is also your quantum number. So for energy n equals to 0 in wave function, you see, if you, even if you restrict n equals to 0, ky has, like, this is your uh, quantum number. So you can see your ground state is like infinitely degenerate, and because ky can have any possible quantum number, so many values, it is possible for ky. So many values are possible. So so in so unlike harmonic oscillator system, the system of charged particle in constant magnetic field, particle in constant magnetic field are are infinitely degenerate for for each distinct values of n. So that is what the key line is. So, like, any question, anything, any problem, you can ask. Uh, so these are like each and every possible eigenstate. I mean, for example, in a harmonic oscillator, for n equals to 0, it is simply half h bar omega, and and corresponding to it, you have only one single eigenwave function, psi 0. I'm just talking about for a single 1D harmonic oscillator. So this is like for 1D harmonic oscillator system. So this H is simply this E0 is simply uh, half h bar omega 0. So this is for 1D harmonic oscillator, like this is true. But for the system which we have, the wave function depends like this. Other than this Hermite polynomial and exponential, it also has, I mean, this exponential decaying or this Gaussian type behavior. But we also have something exponential iky, that is like plane wave behavior. So this tells that our wave function not only depends on this n, so which I was saw here, psi of x or psi of xyz depends on quantum number ky, kz, and n. So for simplicity, we also made kz 0, but we saw that like even if we make kz 0, then we still have this. Uh, Even if we make kz 0, uh, we still have ky. Then because of ky, we if for each n value n equal to 1, 2, 3, for each n value you will find that your wave function psi is infinitely degenerate. And even if you make kz non-zero, then still again it will also become uh, even highly degenerate. So yeah, if there's any question you can ask, anything not clear. Yeah, you can also ask anything other than this also. Yeah, I mean, this is like, as I said, like this is your last problem solving session before your test, and then you are all actually almost done for this course. So you will be having no more live sessions. But yeah, is any other question also you can. Okay, is there any doubt, like Surajit, Samarpita, Rohan, Kuna, anyone? Any question or anything not clear? Okay, if there is no question, then we can like look into the other topic which we missed last time, on time dependent Hamiltonian. I mean, time dependent, uh, basically, let's say time dependent perturbating Hamiltonian. So for time dependent perturbation, so you have remember. Uh, so yeah, so you have remember the Hamiltonians that we have discussed so far, like uh, which were time independent Hamiltonians, or time independent perturbation, like some H naught plus H perturbation. So this was like time independent, but now we have some time dependent perturbation. And so for before going into time dependent perturbation, we have to learn something called how you will solve your Schrodinger equation system. in a different scenario where you have time dependent, which is something called interaction picture. So yeah, so this was used to be time independent before, but now yeah, for time independent system, you also know, like whenever you have time independent Hamiltonian, you can solve your system by uh, using Schrodinger equation, whose solution can be given as something psi of t as exponential minus I h, let's say, yeah, this is h naught t psi, this is psi at 0. So yeah, so but in time dependent perturbation, you cannot just directly do this thing. I mean, you cannot take psi of t as some exponential of I h0 t, because here you also have some perturbation p. But even if you have perturbation p, uh, you cannot take this total h. So you cannot also do this uh, exponential of I h t. H is your total h, and psi 0, because this is only allowed, this is your evolution operator, uh, u of t. This is true only if h is time independent. So this is like in Schrodinger picture. This treatment which we were used to uh, work with is the Schrodinger treatment, but Schrodinger picture. Uh, like there is something called interaction picture. That is how you solve your Schrodinger equation in a different way. That is as follows. So you write your time dependent Schrodinger equation, which is this, and then you define something, a different chi of t. So this chi of t is similar to what we used to do in even in time independent Hamiltonian. This is similar to this time independent Hamiltonian, but yeah, why similar? Because here also you are defining some this evolution operator as something exponential of I h0 t. So here also you have seen, uh, so this will be by h bar. So here also we used to do something exponential minus I h t over h bar, which I said, which is only true if your Hamiltonian is time independent. Here also you can consider this exponential of I h0 only for the time independent part. So you see your h0 is time independent. So this is time independent. So this h0 is time independent, and here also this h is time independent. So and then you can write down your psi as something is just the invert. You just invert this relation, you get this psi of t, and then once you get this psi of t, you put this again, let's call this as something, uh, this is equation a and this is equation b. So b in a will give you this. So so then if you substitute this psi of t in your Schrodinger equation, in equation a, you get, so you just have to take the derivative on the left hand side. So first from the like, if you put the chain rule, this is what the first term would be, and your second term would have a derivative on chi. So then it's basically I can write here, this is h0 plus hp exponential minus I h0 over h bar t chi. So from here you can see this h0 times exponential minus I h0 over h bar t will cancel with this term. So it's basically this term and this will cancel. So then you have only this. So then what you can write from here, you can write. Um, so one thing you remember, you can see there is this factor and this factor. They are also same, but you cannot cancel them. Like this is not, this is completely incorrect. Uh, so why is it? Because these are now operators. Means these are basically matrices. So uh, like what it means basically, suppose uh, you can able to cancel this before also. uh, like, was there any question, anything? Okay, so you were able to like cancel this before because you used to think that exponential of let's say some I h0 or h bar t, uh, exponential of minus I h0 over h bar t equal to, this is one, this is actually identity operator one, this is true. But here if you see like what is the problem, if I uh, multiply, let me call this as equation, like multiplying exponential I h0 over h bar t from left on LHS and RHS both side. So this means uh, I am multiplying exponential I h0 uh, on with exponential minus I h0 over h bar t, which is identity, that is true. So and LHS, that is true, but uh, in RHS it is basically exponential I h0 over h bar t hp exponential minus I h0 over h bar t chi. This is because I cannot also you see here I cannot do this thing like you could have said that like I could have written this something as hp exponential of I h0 over h bar t and exponential of minus I h0 over h bar t, and these two would have cancelled. Like again they would have given identity operator. uh, this is identity and hp times identity is hp, so it is like hp chi. So but this is not true. So this is uh, incorrect. So the reason is like suppose you consider this is actually something matrix A. You consider this is something A. Let's say if I have two arbitrary matrix, exponential A and exponential B, then these are actually matrices. You cannot write this as simply A plus B. This is incorrect. Rather, this is something which is called according to BCH rule. You can check this. This is also probably told in your lectures. If you can also find that. According to BCS rule, this is exponential of a exponential of b is equals to exponential of a plus b plus half commutator of a b, and there are also some other terms as well. So uh, you can write e a e b equal to e a plus b only if commutator of a b is 0. So if commutator of AB is not 0, then there are these terms that will contribute. So earlier, I mean, you used to do this something alpha plus beta is equals to E alpha E beta. Uh, this is again true if alpha and beta are numbers, but if they are matrices or operators, in quantum mechanics we call them operators, then they aren't. Yeah, so this is something, a small information you should note this. So that is why this is what this is actually what it's called BCS rule. You can check this now. So from here, uh, therefore uh, you can write minus IH bar, not minus, this would be simply IH bar del T chi equal to H int and chi. So this H int is basically this. So now to solve then your the complete wave function to compute the solution for this uh, Schrodinger equation, then you have to follow the usual process. But this time you need to be careful that your chi of t is something u int chi of t0, which means if you put this in the Schrodinger equation, you will get IH bar del u int and del t equal to h int u int. So this the solution to this will basically give you chi. So the solution, its solutions are given by something called Dyson series. So that means basically, suppose you consider u int as something uh, u int 0, epsilon u int 1, then epsilon square u int 2. You consider this as a solution for this Schrodinger equation, for this equation, and you solve order by order. So you are basically assuming a solution uh, by order by order. So what does this mean? Like for example, Suppose if I do for order 0 epsilon 0, so I'm talking about u int 0. So for u int 0, so for this order, I'm considering epsilon 0 will be I h bar del u int 0 by del t equal to 0. So you just put this u int in this equation. So just wait a minute. Yeah. So now if you solve the solution for this u int 0, so the solution for this is something uh, uh, some constant. U int 0 is some constant which you can uh, which is basically some identity operator. It's some constant, let's say a times identity operator. So it's because these are all operators, remember, this all things are operators. This u, this chi, and this h, all of them are operators. This is not really um, like required to solve the problem that we will see, but I'm just giving you an idea like what this I mean um, this Dyson series actually gives. So for order epsilon 1, so it would be something I h bar del u int 1 over del t equal to h int u int 0. Then here u int 1 would be something minus I over h bar 0 to t dt prime h int dt prime. Then uh, yeah, then actually if you go on to solve this order by order, then uh, from the second order in epsilon, you would get something u int 2 will give you something I over h bar square, then 0 to t uh, h int, then there are t prime u int 1 t double prime, then dt double prime. So the solution in general, it is something given as something you will see this h int uh, uh, yeah, you can see this h int I this this part is again something which you have calculated here. So it is like you recursively you get a solution, and again this again when you will calculate this u and 3, you will have something u and uh, 2, and inside 2 you will get this 1, and yeah, this will keep on going. So un2 is again related to this, and then un2 is related with un1, and un1 is also. So there are like so many time integrals you can see. So in un3 there is one time integral, unt2 is one time integral, unt1 is also some time integral. So all of this, like, if you take in order, like in proper sequence of time, uh, then the solution is something given as some time ordered exponential 0 to t prime dt prime etc. So in general, this u can be written this un. So that is how your evolution operator behaves in a time dependent type system. So but yeah, but something yeah, we can see an example, but we will not be like going through this Dyson series, which is not required at the moment for the problem we'll see. So think of as let's consider a problem um, as spin-off particle uh, is placed in an external time-dependent magnetic field. Perturbating magnetic field, let's say perturbating magnetic field. So where your magnetic field is B equal to B naught sine theta cos omega t I cap plus B naught sine theta sine omega t j cap plus B naught cos theta cap. So first you need to calculate the Hamiltonian. So to calculate Hamiltonian, so one thing, uh, as we started, like for this time dependent Hamiltonian, your h should be something of h0 plus hp, where your hp is time dependent, your perturbating part. So from the given magnetic field, we have to estimate what is our h, whose what will be your h naught, and what will be your hp. It is the perturbing part of the Hamiltonian. So first, you can uh, start by writing the Hamiltonian. So for a spin-off particle in some extramagnetic field, it is given as something. I think you hope you remember this. This is something magnet dot product of magnetic moment with magnetic field. That is what your energy, even classically you write this relation, that is your like magnetic field energy for a charged particle placed in some extra magnetic field. And you can write this mu, this magnetic moment, as something minus gamma s, because I hope you remember there is something relation between I mean like any magnetic moment you can write it in terms of uh, angular momentum. So here we are writing since our particle is some spin of quantum particle, so we can write it in terms of its own spin s, and this is something as its gyromagnetic ratio. So like if you remember like uh, we write in classic, like this is true classically. Like magnetic field energy is given as something minus m dot b. This is your magnetic field energy. uh, I mean, magnetic field energy associated with the charged particle, and then your magnetic moment m is something, uh, it is given as something, q over 2m, and this is L is angular momentum. So you can think of, if any uh, magnetic loop, which I mean, some current. If some current is flowing through this loop, then it acts like a magnetic dipole, and when you place it in some external magnetic field, so it will actually presses actually. So this is like gyromagnetic frequency, this q by 2m. So this is something classically, you can check your electrodynamics topics, which you have done previously in the past. So from that same thing only, we are writing in terms of quantum mechanical operator and quantum speed. That is just so from there, yeah, I can write this mu dot p as minus gamma s dot p. So now, for the quantum particle which we have, it has some spin s, and it has all the three components, like just like normal angular momentum, sx, I cap, sy, z cap plus sz, k cap dot. Then this entire magnetic field, which is given right here. So this will give you, so before that, like, I can write my sx. These are all, remember, in quantum mechanics, this all these vectors which we are writing, they are operators. So this sx is also your operator, and here also everything, this this b naught sine theta cos omega t, this is also your magnetic field operator. So uh, you remember, this Sx we can write as some uh, form of Pauli matrix. This is h bar by 2 sigma x. This is which we have also discussed previously. For spin of particle, the spin operators are given like this: Sys h bar by 2 sigma y, and Sz equals to h bar by 2 sigma z, and sigma x is actually 1 0 0 minus 1, and sigma y is actually, uh, so this is sigma z. So sigma x will be 0 1 1 0, sigma y is 0 minus I 0. So these are your Pauli matrices. Now, now you can write down your, um, now you can write down your sigma x, I mean your Hamiltonian, as minus gamma b naught over h bar by 2. So yeah, so this, as I said, so this is your first, when you take the dot product, it would be something like, these are your operator sx sy, and also in magnetic field, when you take this as operator, this is like b naught sine theta cos omega t multiplied with identity matrix, and b naught sine theta omega sine omega t multiplied with identity matrix. So this is like, you can write down an identity multiplied with each of this term. So So this will give you something like uh, minus gamma uh, b b naught sin theta cos omega t sx sin theta cos omega t sx, then plus, so minus gamma will be common in all the cases, then you will get something sy, then again something sz. Yeah. So from here, you can write down the complete expression as minus gamma b naught uh, h bar by 2 using the complete matrix form, as it will give you something sin theta cos omega t sigma x plus sin theta sin omega t sigma y plus cos theta sigma z. So this will be like minus gamma b naught h bar by 2 0. If you use the sigma is this matrix, so if you use this, it will give you 0 sin theta omega cos sin theta cos omega t sin theta cos omega t and 0. Then you can use sigma y in the other term, so sigma y is this, so it will give you 0 minus I sin theta cos omega t I sin theta cos omega t 0. Then you have one more term, that is sigma z, which is 100 minus 1, that will give you cos theta 0 0 minus cos theta. So this will be minus gamma b naught over h bar by 2 uh, so your Hamiltonian would be something finally cos theta. If you add this completely, you will find this complete matrix sin theta cos omega t minus I sin omega t, then sin theta cos omega t plus I sin omega t, then minus cos theta. So yeah, and then from here I can simplify a little bit to write it something of this form: minus gamma b naught h bar over 2. uh, I can write this as cos theta, and this is sin theta exponential of minus I omega t. So this is something you know perhaps from the Euler relation. So this is uh, something you have used it many times before. So this is from Euler's relation. You can write this as exponential minus I omega t, and this is sin theta exponential I omega t and minus cos theta. So yeah, from here. Uh, Now, as I said, like I mean, in the question as it is asked, so this is some time-dependent perturbating Hamiltonian. We need to extract out what is perturbating part of the Hamiltonian, which is time-dependent, and the H naught is your time-independent, unperturbed part of the Hamiltonian. So this you can do this in the following way. I can, if I write this as some diagonal term, some diagonal matrix E10 E2 plus some k is your k times 0 exponential minus I omega t and exponential I omega t 0, where E1 is minus gamma bh bar by 2 cos theta, and E2 is gamma bh bar by 2 cos theta, and your k is minus gamma b naught h bar by 2 sin theta. So now this is your uh, this is your HP part, and this is your H naught, which is time independent. Yeah, so this is what your perturbating part of your Hamiltonian, k times 0 exponential minus I omega t 0, and your H naught, which is E1 0 E2. This is time independent. Now from so this is what the first thing you need to do here. Uh, and second, let's say the second part of the question is, is this clear or any question, any doubt? If not, please ask something. Uh, the next you have to determine chi uh, with the help of interacting Hamiltonian, that is Hi, the Hi which we defined before here. So uh, this is only Hi. Like, or let me write this as H int. Then uh, assume your initial state, that is chi at 0, at t equals to 0, is it is the upstate for the SZ basis for the this means your this is like spin up state in SZ basis. When you write this state in SZ basis, so this is your spin up state. I can write it as spin up state in SZ eigenbasis. This normal spin up spin down, which we have discussed a lot of times before. Uh, so now, uh, yeah, so you need to determine what is chi. So for chi, as I said, you remember, uh, to determine chi, we have to basically uh, solve this equation where this H is given by this Hamiltonian. So it's the perturbing part of the Hamiltonian which is transformed using this exponential operators. So these exponential operators, you see, they contain H0, which is unperturbed part. So this whole thing has information about both perturbative part of your Hamiltonian and your unperturbed part of Hamiltonian. So using this, we have to find the solution for this equation, which will give us chi, and chi is something which we want to calculate. So first we can, uh, yeah, your first you need to calculate h in. So to determine chi, we have to solve del by del t chi of t, which is h in chi of t. So your h in is basically exponential of minus I h0 over h bar t, h perturbative part, then exponential of I over h naught over h bar t. So we have already calculated what is our h0. So this is h0. So using this h0, so and you see h0 is a diagonal matrix. So for any diagonal matrix, h0 is diagonal. That means h0 is e1, 0, e2. For any diagonal matrix, you can write this exponential of minus I h naught by h bar t. You can write this as exponential of minus I e1 over h bar t, 0, 0, exponential of I e2 over h bar t. So you can write this only if your matrix is diagonal. Otherwise, to write an exponential of any matrix, you first diagonalize it and then you can write it like this. This is the way to write the matrix exponential of any given matrix or Hamiltonian, any matrix. Then so you first got what is your exponential, and then you can also find what is exponential of this as well. So which is just the same thing but only differs by sign. And HP we already calculated before. So now you can calculate your complete HN. So this is HN. It's basically yours. Uh, there will be common factor of k from which will come from HP. So then you have this matrix exponential of minus I e1 over h bar t, 0, 0, and exponential of minus, this will be minus I e2 over h bar t. Then hp as we calculated before, so there will be k multiplied with the matrix 0, exponential minus I omega t, exponential I omega t is 0. Then you also have the other, uh, uh, this will be exponential of I e1 over h bar t. then 0 exponential of I v2 h bar t, right? So then if you solve this, again you will get something your h in. You do the matrix multiplication, and after doing so, you will, you can easily see that you will find something of this relation: exponential of I omega 0 minus omega t, then exponential of minus I omega 0 minus omega t 0. So this is your Hn. Now, using this Hn, we have to find out what is chi. So chi is your solution. Uh, Chi equal to, uh, I can write down one more step which was there. So if you solve this, let me take this down here. So it would be like, so after doing the matrix multiplication, it is something, you will get something 0 exponential minus I e2 minus e1 over h bar t minus I omega t, and here you will get minus I e e2 minus e1 over h bar t plus I omega t, where e1 is like minus gamma b naught h bar by 2 cos theta, and this I'm writing as omega naught by 2, omega naught by yeah, this is like omega naught by 2, and uh, h bar omega naught by 2, yeah. And so it's when I do e2 minus e1, it is omega naught h bar, because e2 is negative of e1, right? So finally omega naught h bar is uh, gamma b naught cos theta h bar. Yeah, so from there, this is what your final agent will come out. So then using this agent, you have to determine what is chi. So we know, you have to calculate d dt of chi is actually agent chi. So uh, let's uh, take chi as something, chi of t as something c1 of t and c2 of t. Then so there will be I h bar. So it will be I h bar d dt c1 of t c2 of t. Yeah, this is a bit long, but the way to do is something this. So you do not have to do the Dyson series which I was talking about here. So because we are solving directly from the uh, this matrix algebra, we are considering some C1 and C2 as the solution, and we'll see, we have to calculate what is C1 and C2, and so C1 and C2 is calculated, then chi is known for it. So I omega naught minus omega t, this is minus, these are HP not minus. So sorry, this is H int 0 C1 of t and C2 of t. So from here you will get two different equations. One IH bar dc1 by dt equals to k exponential of I omega naught minus omega t C2, and you will also get IH bar dc2 by dt equals to k times exponential minus I omega naught minus omega t C1. So you see these two equations are coupled differential equations. So for coupled differential equation, you have to first decouple them, then you solve the differential equation. So uh, to decouple them, like you take derivatives on both the equation. So take derivatives on both differential equation to decouple them. So it is, so if you take uh, uh, so derivative on this equation, so first take derivative on this one. So in LHS you will have second derivative. It is like uh, d square c1 by uh, dt square. You will get on the right hand side. You again have to take derivative from there. You will get minus ic I omega naught minus omega exponential I omega naught minus omega dc2 plus exponential I omega naught minus omega t dc2 by dt. And so here you can use minus Ic. Uh, so this will be z times omega naught minus omega exponential. Uh, yeah, this is exponential I omega naught minus omega, uh, or tc2, then minus Iz exponential I omega naught minus omega dc2 by dt. Then use dc2 by dt, which uh, we know from here. You can use dc2 by dt from here, uh, or basically you can also use, or it's better to use, uh, use c2 from from the first equation, from this equation itself. So if you use c2 from here, you can easily get this differential equation d square c1 dt square equals to uh, I omega naught minus omega dc1 dt minus g square c1. So here you are using uh, c2s from here. C2s this thing. So so it is like I h bar by k exponential minus I omega naught minus omega dc1 by dt. Yeah, if you use this over here, this is what you'll get. So then you can see you have reduced, decoupled your first differential equation, and same way you have to decouple the other differential equation. So this is decoupled. So dt square. So yeah, if when you decouple the other differential equation, it would be something I omega naught minus omega dc2 over dt plus g square c2 equals to 0. Then these are your standard ordinary differential equation, and I hope you know the solutions to them. Like for example, solution to this would be something like c2 of t as some constant a plus I alpha plus t plus a minus exponential minus I alpha minus t. So this is how normally you write. Uh, like for example, if you have y double prime plus alpha y prime plus beta as your some differential equation, so you write y is in this way: a1 exponential I some, let's say, uh, so this is let's call this as uh, this a and b. This is a and b. So you write it as something alpha plus t plus or a2 I alpha minus t equal, yeah, this is what you write the solution, where alpha plus is given as something the root of this auxiliary equation, which is something minus a plus or minus uh, a square minus 4b over 2. Yeah, that is what I mean. I hope you know this from your mathematical courses, from uh, mathematical methods courses. So from there, this is just that simple solution. So similarly, you will also have solution for this differential equation. So these are your ordinary differential equation in second order. So here alpha plus will be, so your alpha plus will be alpha plus minus 4 is minus omega naught minus omega plus minus omega naught minus omega square plus 4g square over 2. So then the last thing which you need to find here is the initial, yeah, similarly you will also have c1t. For c1t it is like you can write it as 1 over z exponential I omega naught minus omega t dc2 by dt. So this is like c1 of t 1 over z exponential of I omega naught minus omega t. So dc2 over dt. So using this c2, you can calculate what is dc2 over dt. This is your dc2 over dt. So using here, you can calculate what is dc2 over dt. From there, you will get what is c1. So c1 is this. So this derivative will give you ia plus alpha plus exponential I alpha plus t minus I a minus alpha minus e I alpha minus t will be minus. So you got C1 and C2. Then initial condition you have to use as it is given in the question also. Initial condition is given as C1 of t equal to 0 is uh, 1, and C2 of t equal to 0 is 0, because chi 0 and initial is given as upstate, that this is 1 0. So that is why C1 equal to 1 and C2 equal to 0. So you got your initial state. So using this initial state, you can calculate your chi of t. Your C1, C2 already calculated. You just have to estimate what is A plus and A minus. So so if you use this initial condition, your A plus will give you G by alpha minus minus alpha plus, and A minus is minus of A plus. So finally, you can write down your final answer is 1 over z exponential I omega naught minus omega t I A plus uh, alpha plus exponential I alpha plus t minus I A minus exponential I alpha minus t. There will be alpha minus here, right? Then C2 will be this A plus I alpha plus t plus A minus exponential minus I alpha minus t. So yeah, so these are your C1 and C2, your solutions, where A plus and A minus is this. Yeah, so that was what for this. Like it was long, but yeah, but this is how time dependent systems becomes like really complicated. Your time dependent perturbation. So you need interacting Hamiltonian. The two things we needed. So one was your interacting Hamiltonian. This HI. I mean, it's particularly this interacting Hamiltonian. Using this only, we calculated what is chi for here. And now, to calculate what is psi, to calculate psi, at the beginning we have said psi is something exponential I h0. This is your time independent part multiplied with chi. Basically, it is operating with chi. So this is your time independent part. So if there is any question, any problem, it so it will be like a mix of both. Like I mean, you will have. I mean, you won't be have like having to do all of this, like how we are solving this here. So these are like some detailed discussions we were doing. But like in exams, like if there is some objective questions, like don't get worried with that. Like it would be something like two. I mean, few step calculation. It won't be this. I mean, big, or you won't need any. I mean, some extensive workup. Is just briefly you can state the results. So it's better like if you go through your assignment problems once again. That will give you a better idea, and it will be more or less like you will find your questions would be similar to that. So and also there would be many multiple number of this objective type questions also. So it would be fine. So no need to like worry about, like no need to take much stress about. Just go through the uh, assignment problems particularly, and yeah. Okay, so there any other question, anything? Okay, well, I hope you have found this course useful to you. This has been your end of your course. I mean, you are only left to appear for your test, and then you will be finally concluding your course. So you have probably you have enjoyed this course. This would be a little typical course in regard to what you would expect, like how I mean, in general, what quantum mechanics is about. Like, you have seen a lot of cases, like, I mean, in this I mean, you have seen a lot of like bit of diverse topics, like in there were topics from quantum information, there were topics of related with this perturbating theories, and there were topics also, like on various application sites, like this new magnetic resonances, NMR systems, and all that. So, uh, like the topics which are covered in this course is really important in many aspects. It gives you various options. Uh, there are topics ranging from like various optional application areas, and you will find this like at any point, like you will find the course to be useful, because even if you do some uh, research or go into some particular engineering field, because most of the days it is all about using quantum technologies, and you'll find somewhere some principles would help you to realize which you have found it here. And also, if it is a uh, like if you are planning to do something, some sort of research in physics itself, then uh, you are almost there for a treat, because I mean, all of the thing which you have found in this course will be come into use. And yeah, so uh, so that was for also for all the problem solving sessions which we had. So I hope if any problem is there, you can like contact, like maybe in the forum which is there, like we can communicate there. And uh, yeah, that was for this problem solving session as well. And let's see if we can meet again in some any other course, and NPTEL. If you register, then hopefully if I'm also assigned there for this problem solving session, then we can hopefully meet and have discussion more in the future. So yeah, that was with this problem solving sessions. And uh, like hope all the best for your tests, and like do well. So it would be a like nice, I mean, don't take much stress on that. So yeah, so fine, uh, let's go. If there is no other question or anything, we can end the session. If there is, then we can. Okay, if there's no more question, then yeah, fine. Goodbye. Like all the best for your test.